Hello, my name is John McCormack and I'm from SensiLab at Monash University in Melbourne, Australia. And I'm going to present this paper on the Enigma of complexity. This is joint work with my co-authors, Camilo Cruz Gambardella, who's also from SensiLab at Monash University in Melbourne, Australia, and Andy Lomas at Goldsmiths, University of London in the UK. In this talk, I'm going to look at both the conceptualization and the measurement of complexity. More specifically, visual complexity in the context of creating generative and evolutionary art. And a natural question to begin with is to ask, what do we mean by complexity? Now, of course, we have an intuitive understanding of what it means to call something complex. As this map of Rome by Gian Battista Nolli, drawn in 1748, shows, a complex image has many different components that have some visual connection or form. And perhaps our impression of complexity is enhanced by knowing that this is a map of a large and complex city that we may have experienced firsthand. We can see details at multiple scales. The connections between elements are nuanced and varying. We would need to study the map carefully, giving it our full attention to navigate from one part of the city to another, for example. Now, this image is of an architectural model created in 1968, and it illustrates complexity in a different way. The work is a product of the partnership between the architect Claude Parent and the philosopher Paul Virilio. They called themselves Architecture Principle. At first, it appears deceptively relatively simple, a collection of similar oblique forms that are stacked in a repeating pattern that builds in layers from the left to the right. However, closer inspection leads to more details and nuances in each individual form, including stairways and pathways between elements and contrasting areas of form and void. The layered stacking is almost generative in nature, suggesting that the stacked layering could easily be progressed, the form growing in scale from left to right. We can also think about complexity in art with these two examples of well-known paintings from the 20th century. On the left, Lucio Fontana's Cut, the simple gesture of creating a slit in a framed, untreated canvas, illustrates both a simple, powerful aesthetic, yet conceptually complex interpretation that even what might be considered visually simple art can evoke. On the right, Jackson Pollock's 26A shows a visual complexity that rides the edges of randomness and form, asking us to consider the differences between randomness and complexity, a topic that we'll examine in more detail. The other question we need to consider is the relationship between complexity and aesthetics. What is the relationship between visual complexity and aesthetic appeal? Well, it turns out, as many of you probably already know, that this is not a new question. And of course, mathematicians and psychologists have all had a go at devising an aesthetic measure seated in the relationship between complexity and order. Birkhoff's famous measure used a simple ratio of order to complexity, and he identified three phases of aesthetic appreciation. First, the effort of attention to perceive the object, which increases proportionally to its complexity. That's labelled C. Second, the feeling of the object's aesthetic value arising from this effort, labelled M. And third, verification that the object is characterised by a certain harmony, symmetry, or order, O, necessary for the aesthetic effect. Berlin similarly looked at the relationship between pleasantness and complexity, and based on earlier work by Wundt, devised a temporal relationship between hedonic value and arousal potential in aesthetic appreciation of an object. And of course, there are many others who have tried to formalize these relations using more recent mathematical and physics techniques, such as information theory, entropy, and even fractal dimension. There are two excellent papers by Greenfield and Honig that give overview of the history of aesthetic measure, so I won't go into a long history here, but it's worth highlighting two important contributions relevant to the work in our current research that I'm presenting today. The first is the measure proposed by Machado and Cardoso that defines the complexity of an image as the ratio of the image complexity to the processing complexity, with image complexity defined as the ratio of the RMS error of the compressed and uncompressed versions of the image and the amount of compression achieved on the image. And here for compression, we're talking about a lossy compression system such as JPEG. The reason these are used is that they are considered a reasonable proxy for information complexity. And several years ago, Den Hilger and Eben used 4 different aesthetic measures in a simple evolutionary art system to see how effective each measure was as a fitness measure, including the Machado-Cardoso measure. They found that different measures in combination produced the best results. All right, so now down to the work we have done. We wanted to understand how useful complexity measures might be in helping visual artists. For example, can they be used in an evolutionary system to predict how interesting or appealing a particular visual form might be? Or could they be used to filter out candidates that are just not visually appealing because they lack visual complexity? We looked at 10 different complexity measures that can be applied to images to see how well they might reflect an individual artist's aesthetic evaluation. Here's the full list of the 10 measures we used. I'm just going to highlight a few here, but they're all described in detail in the paper. Some measures, such as image entropy, look at the distribution of intensities in an image. Some are morphological, such as the Euler measure, which looks at the number of contours needed to describe component boundaries. A number of measures use image compression methods to get a measure of the information complexity of an image. The most recent in this category is the measure devised by Lackhall and colleagues, which uses compression ratios but pre-filters high-frequency spatial and intensity noise from the image before measuring. They refer to this measure as the structural complexity and achieved high correlation between this measure and human aesthetic evaluation, but only using a set of abstract synthesized images, not images that would be considered aesthetic or artistic. This was indeed deliberate, as the research focused only on image complexity and aesthetics. For our experiments, we used 3 different data sets, all of which we've made publicly available so others can use them too. And as a side note, when embarking on this work, we found that while there are numerous image data sets and even art image data sets that are freely available, there are almost no computer-generated art data sets available to researchers, which may be why in many published papers, people use their own simple toy systems or resort to generating their own images. We are firm believers in the use of ecological validation of creative and artistic research. That is, if you are trying to understand a creative practice or artistic process, you need to work with real artistic images or examples in ecologically valid settings that artists actually use, not in controlled laboratory setting or by using synthesized proxies. Anyway, on to the data sets. So this is the first one. It's by the award-winning computational artist Andy Lomas, one of the co-authors of this paper. It consists of around 1,700 individual morphogenetic 3D forms rendered as 2D images. Each form also includes an artist-assigned aesthetic ranking score, which is an integer in the range 0 to 10, and a categorization for each image. For the work I'm talking about today, we only use the aesthetic ranking information, not the categorization information. The second data set is a series of 53 line drawings created using a niche construction method. These images are from a work I did several years ago. They use an agent-based evolutionary model and include a normalized aesthetic ranking for each image. The third data set consists of 2,500 evolved 3D forms generated using a differential line algorithm. The 2D layers at each time step are stacked on top of each other to generate the 3D form. This 3D form is then 3D printed to create a physical structure. For this data set, we computed the geometric complexity directly from the 3D geometry. The complexity measure is based on the amount of physical variation in each layer of the model. Now, the reason for doing this is to compare the physical complexity of a 3D object with respect to the 2D image of that same object and its visual complexity. For example, in the Andy Lomas data set, the forms generated are 3-dimensional geometries, but the human evaluation is done on 2-dimensional image renders. We wanted to test the assumption that 2D representations of 3D forms are a reasonable proxy for aesthetic judgment of the physical 3D form. One motivation for doing this is that the physical complexity calculations are often very time-consuming for 3D models, whereas image complexity calculations are fast and efficient in comparison. This slide shows the 2D rendering and the corresponding 3D printed form. In some cases, the form fails to print, usually because there is insufficient support from a preceding layer when the form has been 3D printed. We eliminated these forms using a formalized measure of printability, which measures how successfully the form will print. By eliminating these forms with low printability scores, we didn't end up with any unprintable forms. So here you can see some examples of successfully printed forms, and these are photographs, not renderings. Remember, we are not evaluating photographs of the printed forms, only the 3D lines rendered as 2D images. Okay, so now onto the results. We ran each of the 10 complexity measures that are image complexity, visual complexity measures on every image in the data set and computed the Pearson correlation between each measure and the artist-assigned aesthetic score. So for the Andy Lomas data set, the results are shown in this slide. The column highlighted in blue shows the measure with the highest correlation. You can see here that for the Lomas data set, the Machado-Cardoso measure gives the best result, a correlation of 0.873, which is a pretty strong correlation. Plotting the relationship between this complexity measure and the score shows a fairly linear relationship, but there are, of course, some outliers and variation, as this is only a linear correlated measure. On the right, the relationship between the Machado and Cardoso measure and Lacroix et al.'s algorithmic complexity measure, both of which are very similar in the way that they compute the complexity of the visual complexity of the image. Here it's easy to see why both measures are highly correlated to each other, but the Lacroix measure is not so linearly correlated to aesthetic score as the Machado and Cardoso measure is. So I think the takeaway from this is that actually algorithmic image complexity measures are a pretty reasonable proxy for Andy Lomas's aesthetic evaluation, and indeed could be used to help him find forms that he thinks have high aesthetic value, or at least reject those which don't have high aesthetic value. So now here are the results for the 3D forms dataset. While not as impressive as the Lomas dataset results, there is still a high correlation between the structural complexity measure and the physically computed form complexity. Recall that the structural complexity measure filters high-frequency spatial and intensity detail, and one of the tricks about this measure is that you need to work out the appropriate values of the coefficients for this filtering before performing the measure. The authors of the original paper used different values for different data sets, apparently reached through a trial and error approach. We adopted a similar approach, finding that there's reasonable latitude in varying the coefficients, and it's best to use the image resolution as a guide for how to set those coefficients. Here we can see the relationship between the score, or the complexity, the measured physical complexity, and the structural complexity measured on the 2D image. And again, a clear linear trend is visible, but with some variance. One surprising result was how poorly the fractal complexity measures performed. This was quite unexpected, as there are a number of publications that support the relationship between fractal dimension and complexity and perceived aesthetics. The plot on the right shows the relationship between score and the fractal dimension measure. The measure uses the box counting method and then maps the raw fractal dimension to a Gaussian curve, maximized at a fractal dimension of 1.35. This value was chosen based on previous findings described in the literature as being the sweet spot for fractal dimension and aesthetics. You can see that there is some clustering of medium complexity individuals that all have a relatively high fractal complexity score. Looking at these individuals showed a number with branching structures, indicating that this measure might be a good way to emphasize branching in the generative system. But of course, it wasn't a very good way of understanding the complexity of the 3D form in total. So the last result here are the results for the line drawing data set. And here, the morphological complexity measures give the best results, which is unsurprising, as they're basically counting the number of distinct morphological features using contours. But the correlation is only mild. It's also interesting to observe here that algorithmic complexity measures performed the worst. After running this experiment, we tried an additional measure on this data set, image skew. This basically measures how skewed the intensity histogram is for each image. And given that the drawings are based on niche construction, which tries to maximize the diversity of high and low density regions in each image, it seems reasonable that this measure performs better than any of the other complexity measures that we used. Because this data set is relatively small, with only 53 images, we can look at visually ordering the entire data set by different measures. On the slide, we see the same data set. On the left, it's ordered by artist-assigned aesthetic evaluation, and on the right, ordered by structural complexity as measured from the 2D image. The ordering runs from left to right, top to bottom. So the lowest value, top left, and the highest value is at bottom right. It's fairly easy to see increasing visual complexity for the ordering on the left. On the right, however, it seems to me at least that any structural ordering is far less apparent. This might have something to do with high-frequency detail being filtered, but it demonstrates that just naively applying these measures is not always going to work or be useful. Okay, so what did we learn from all of this? Well, should you use complexity measures in your generative art system is the big question on everyone's lips, I guess. And based on our experiments, I think the answer is a qualified, that depends. First, these measures are relatively quick and easy to compute. You don't need a bank of GPUs or TPUs like you do for deep learning, for example. The next point is that they work on 2D images, so are agnostic about the generative system or the method of generation. As long as you can generate a 2D image, you can apply one of these measures. Our findings indicate that there is no single best measure, but if you choose a measure carefully, it can act as a reasonable proxy for human aesthetic judgment. So it can be a useful part of a fitness evaluation or fitness measure in an evolutionary system, for example, or as a filter in a generative system. And this could end up saving you a lot of time and hence potentially give you much more interesting results. However, as the saying goes, and the paper as well, there is no free lunch. And we've only tested 3 distinct data sets, so we can't draw any universal conclusions from these results just yet. All right, so what about other methods, you might ask? Well, for the Andy Lomas data set, in a previous work presented at EvoMusArt last year, Andy and I trained a convolutional neural network to predict how much Andy would score and categorize an individual one of his 3D forms. The resultant network was able to do that with very impressive accuracy, particularly given the subjective nature of aesthetic evaluation. However, there are 2 problems when you come to use deep learning. The first is that you need a large training set, and this must include artist-assigned aesthetic scores or categories, which is very time-consuming to do. Andy spent months evolving and assigning the metadata to create the data set we're using, so it's not a trivial task. The other issue is that training requires a large number of GPUs or TPUs to do in a reasonable amount of time. So your electricity bill and potentially the environmental cost of using such technologies may be significant. There's also another factor that is important. How much of an aesthetic judgment and aesthetic experience comes only from the object being judged or experienced? Because this is the only thing that we're measuring. The diagram on this slide is from a paper by the psychologist Leader and his colleagues. It summarizes their model drawn from psychology and neuroscience research of how aesthetic judgment is formed. Perceptual analysis and hence measurable properties of the object, such as complexity, symmetry, and so on, are only one small part of the overall model. It also includes the observer's prior experience, cognitive mastering, domain knowledge, and the viewer's affective state. This is one of the reasons why, in this paper, we used individual personal aesthetic evaluations rather than collective evaluations. The aim was to keep these external, non-object contributions to aesthetic experience constant for every evaluation. A recent survey paper by Skov summarized aesthetic appreciation from the perspective of neuroimaging research. Here's one of the key findings. Aesthetic appreciation is not a distinct neurobiological process assessing certain objects, but a general system centered on the mesolimbic reward circuit for assessing the hedonic value of any sensory object. Another important finding was that hedonic values are not solely determined by object properties. They are subject to numerous extrinsic factors outside of the object itself. So, to conclude, it seems clear that current research shows that aesthetic judgment is not the sole property of an object or image, so any aesthetic measures we devise need to take this into account. Our study found that complexity measures may have some benefit if chosen appropriately, but cannot completely replace human judgment and discretion. We are currently undertaking a survey that aims to see how audiences' judgments about complexity and aesthetics correlate with the artist's personal ones, and we hope to include this in a study in an updated version of this paper later in the year. But for now, complexity remains an enigma in our understanding of what makes generative art appealing. Thanks for listening to the presentation.